Hello. In today's lesson, Candace and I are going to talk about solving linear equations that have only one variable. And then Anne is going to work a few applied problems involving both linear equations and linear inequalities. I'm going to begin by reviewing the concept of solution sets to inequalities. And then I'm going to talk about the addition property of inequalities. Turns out there's an addition property for inequalities that's a whole lot like the addition property for equations. Then I'm going to talk about the positive multiplication property of inequalities. And then I'm going to segue to Candace so that she can talk about the negative multiplication property of inequalities. And then Candace is going to put it all together for you. So first, let's review solution sets to inequalities. Let's consider the inequality y is less than 7. Let's graph the solution set, state the solutions to the inequality, state the solution set using set builder notation, and state the solution set using interval notation. So to graph this, I need to begin with a number line, and I need to make sure that one of the points on the number line is 7. I also need to indicate that this is a y number line since the variable in my inequality is y. 7 is the endpoint of the solution set to the inequality, but it's not included in the solution set, so I need to put an open circle at 7. Y is less than 7 means y lies to the left of 7 along the number line, so I need to go ahead and shade to the left of 7 and put an arrow indicating that this interval never stops to the left of 7. Now, the solutions are any number that lies to the left of 7. Any number that lies to the left of 7 on the real number line is a solution to this inequality. 2 lies to the left of 7. 2 is less than 7. 2 is a solution to the inequality. Using set builder notation, the solution set is written as the set of numbers y such that y is less than 7. Using interval notation, we say that the solution set is the open interval that has no left-hand endpoint, which we write and read as negative infinity, and that has a right-hand endpoint of 7, but 7's not included, so we have a parenthesis there. Since neither endpoint is included, there's really only one in the first place, we call it an open interval. Now I'm going to introduce something that's called the addition property of inequalities. Let's recall that two equations are equivalent if and only if they have the same solution set. So for example, the equations x equals 2 and x plus 1 equals 3 are equivalent because the solution set for each equation is the set whose only element is the number 2. 2 equals 2 and 2 plus 1 equals 3. Well, we have a similar definition for equivalent inequalities. Two inequalities are equivalent if and only if they have the same solution set. Let's explore this idea by starting with the solution set. In Figure 1, I've drawn a solution set. Let's state 3 different inequalities whose solution set is illustrated in Figure 1. Well, the first thing I'm noticing is that the endpoint to the solution set is 2, but since there's an open circle at 2, 2 is not included in the solution set. The solution set includes all the numbers to the right of 2. Now, I see that we have an x number line, so when I state my inequalities, I want to make sure that I use the letter x. Since x lies to the right of 2, one inequality that has this as its solution set is the inequality x is greater than 2. Well, if x lies to the right of 2, it's also true that 2 lies to the left of x. So another inequality that has this as its solution set is the inequality 2 is less than x. I'm also thinking, if I take a number bigger than 2 and subtract 2, one thing's for sure, the result's going to be greater than 0. For example, 2.1 minus 2 is 0.1, which is greater than 0. On the other hand, if I'm on the other side of 2 and I subtract 2, the result's going to be less than 0. 1.9 minus 2 is negative 0.1, which is less than 0. So something that all of the numbers that are to the right of 2 have in common is that x minus 2 is always greater than 0. Since these three inequalities all have the same solution set, these three inequalities are all equivalent inequalities. Now let's explore the first and last inequalities of these three inequalities in a little more depth. Let's consider the inequality x minus 2 is greater than 0. What algebra might establish that this inequality is indeed equivalent to the inequality x is greater than 2? Well, before exploring that question, let's consider this question. Let's first consider the equation x minus 2 equals 0. What work did we show to establish that this is equivalent to the equation x equals 2? We added 2 to both sides of the equation, and we ended up with the equivalent equation x equals 2. So what work might establish that x minus 2 is greater than 0 is equivalent to x is greater than 2? Maybe we can just add 2 to both sides of the inequality. So let's start with our original inequality. X minus 2 is greater than 0. Let's add 2 to both sides of the inequality. The left side simplifies to x. The right side simplifies to 2. So sure thing, we ended up with our equivalent inequality, x is greater than 2. What I just used here is what we call the addition property of inequalities. One way we can say an addition property to inequalities is that a is greater than b if and only if a plus c is greater than b plus c. Here the letters a, b, and c could represent numbers, or they could represent other types of algebraic expressions. Let's explore this graphically. Here I have a number line, and I've randomly picked 2 points with the property that the point on the right is named a and the point on the left is named b because I'm trying to establish a relationship that a is greater than b. Now for the moment, I'm just going to refer to these as the purple point and the green point. If I were to move both of these points right, say 4 units, since both points are being moved the same distance, the purple point is going to stay to the right of the green point. What I've just done is I've added 4 to both a and b. So if a is to the right of b, a plus 4 is also to the right of b plus 4. I have shown that if a is greater than b, then a plus 4 is also greater than b plus 4. Now it turns out that the addition property of inequality is valid regardless of the initial direction of the inequality sign and regardless of whether or not the endpoint is included in the interval. So there's really 4 addition properties of inequality. The addition property of inequality also applies to subtraction because subtracting a number is the same as adding the opposite of the number. So holy smokes, our 4 properties have now turned into 8 properties. Let's see if we can get this back to just 1 property. And the best way to do that is with a verbal model. The addition property of inequalities. Adding or subtracting the same number from both sides of an inequality does not change the solution set to the inequality. Another way of saying the exact same thing is that adding or subtracting the same number from both sides of an inequality results in an equivalent inequality. And the reason this is saying exactly the same thing is because the meaning of equivalent inequalities is that the 2 inequalities have the same solution set. There's yet another way of saying this. Adding or subtracting the same number from both sides of an inequality does not change the sense of the inequality. That is, Adding or subtracting the same number from both sides of an inequality does not change the direction of the inequality sign. Those two sentences have exactly the same meaning. The sense of the inequality is directly implied by the direction of the inequality sign. This is the way I like to remember this addition property, that adding or subtracting the same number from both sides of an inequality does not change the sense of the inequality. You just want to remember it in whatever manner makes it work for you. Let's use this addition property to solve the inequality t plus 4 is less than or equal to negative 2. Just like if we were working with an equation, we'd want the t to stand alone. In this inequality, we want the t to stand alone. All we need to do to achieve our objective is subtract 4 from both sides of the inequality. And when I do that, I'm left with the equivalent inequality, t is less than or equal to negative 6. So it appears that our solution set is the set of all numbers to the left of negative 6 in addition to the number negative 6. But just like with equations, we want to check this answer. So how are we going to check the solution to a linear equation in one variable? Well, it turns out we have to make two checks. The first thing we need to do is we need to make sure that the endpoint of our solution set makes the expressions on either side of the inequality symbol equal. We need to do this regardless of whether the equality is included in the inequality symbol. The endpoint, if it's correct, will always make the two expressions on either side of the inequality symbol equal. Then what we need to do is we need to also check some number in our proposed solution set to make sure it produces the proper sense of inequality. And the number we use in this check cannot be the endpoint of our interval because, as I just mentioned, at the endpoint, the two sides of the inequality symbol are actually equal to one another. Now, that was a lot of words. Let's see some examples to make sense out of all that. So our proposed solution was the set of numbers to the right of negative 6 in addition to the number negative 6. The first thing we need to do is check for equality at the endpoint of our solution set. The endpoint is negative 6. So let's see what happens when t is negative 6. If t equals negative 6, our variable expression t plus 4 evaluates to negative 6 plus 4, which is negative 2. When t is negative 6, the two sides of the inequality are equal. That's what's supposed to happen at the endpoint of the interval. So that's a check. Now we need to check for the proper sense of inequality at an interior point on our solution set. An interior point of the solution set is any point other than the endpoint. So I'm looking at my solution set and I'm seeing that negative 8 is one of the interior points of my interval. So I'm going to go ahead and test t equals negative 8. If t equals negative 8, then our variable expression, t plus 4, evaluates to negative 8 plus 4, and negative 8 plus 4 is negative 4. I'm not done with my check yet. I need to check the sense of the inequality. How does negative 4 compare to negative 2? Well, on the number line, negative 4 is to the left of negative 2. So negative 4 is less than negative 2. When t is negative 8, the resultant numbers create an inequality that has the same sense as our given inequality. So this checks. Our solution is valid. So let's go ahead and state our solution set. The solution set is, now if we're working a problem on a test and there's directions that say state your solution set using set builder notation or state your solution set using interval notation, you need to make sure that you use the proper notation. If there is no such specification, you can choose whichever notation you want. If we choose to write the solution set using set builder notation, it's going to be the set of numbers t such that t is less than or equal to negative 6. If we had chosen to write our solution set using interval notation, well, the interval has no left-hand endpoint, so we're going to begin with our open parenthesis negative infinity. The right-hand endpoint is 6, negative 6, indeed. And since we're including that endpoint, we want to use a square bracket to indicate inclusion. Now I'm going to talk about the positive multiplication property of inequalities. I have a table here, and in the left-hand column of the table, I have indicated several numbers and each pair of numbers has the property that the number on the left is less than the number on the right. In the second column, I've multiplied each number in the pair by 2. And what I'm going to do is compare the relationship between the results of multiplying each number by 2. For example, in my second row, I'm saying that 3 is less than 10. When I multiply 3 and 10 by 2, I get 6 and 20. And the relationship between 6 and 20 is that 6 is less than 20. In the third row of the table, I'm saying negative 2 is less than 6. When I multiply those two numbers by 2, the results are negative 4 and 12. Negative 4 is less than 12. In the final row of my table, I'm saying negative 7 is less than negative 3, which is true because negative 7 lies to the left of negative 3. When I multiply these two numbers by 2, the results are negative 14 and negative 6. Negative 14 along the number line lies to the left of negative 6. So negative 14 is to the left of negative 6. In all three cases, I started with the relationship A is less than B. In all three cases, when I multiply both sides of the inequality by positive 2, I ended up with a less than symbol. In other words, 2a is less than 2b. Multiplying both sides of the inequality by positive 2 is not changing the sense of the inequality. This is an example of a positive multiplication property of inequalities. A is less than b if and only if a times c is less than b times c. This is at least true where c is greater than 0. Let's use the addition property of inequality to establish that if a is less than b, then 2 times a is less than 2 times b. This is going to be sort of like a proof. You don't need to worry about ever having to replicate what I'm about to do. I'm just going to try and convince you that it's really true that if a is less than b, then 2 times a is really less than 2 times b. Candace is going to do something later on to try and convince you of something that's a little more startling. So we're going to start off with this comfortable example here. So I'm going to start by saying, suppose that A is less than B. Then by the addition property of inequality, it follows that A minus B is less than B minus B. So when I simplify the right-hand side of this inequality, we get A minus B is less than 0. There's a verbal description for the relationship that A minus B is less than 0. And that is that A minus B is a negative number. So now what I'm going to do is I am going to take this negative number and I am going to multiply it by positive 2. 2 is a positive number. A minus B is a negative number. When you multiply a positive number by a negative number, the result is a negative number. With inequality symbols, we can describe the fact that 2 times A minus B is a negative number by writing 2 times A minus B is less than 0. Let's go ahead and distribute the 2. That gives us 2A minus 2B is less than 0. Let's go ahead and add 2b to both sides of the inequality. So now we have 2a minus 2b plus 2b is less than 0 plus 2b. And when we simplify, we're left with 2a on the left, 2b on the right, and we're saying that 2a is less than 2b. So it is, in fact, a fact that if a is less than b, 2 times a has to be less than 2 times b. So let's state the positive multiplication property of inequalities in words. Multiplying both sides of an inequality by the same positive number does not change the solution set to the inequality. Another way of saying exactly the same thing is that multiplying both sides of an inequality by the same positive number results in an equivalent inequality. Two inequalities are equivalent if and only if they have the same solution set. I like to remember the property this way. Multiplying both sides of an inequality by the same positive number does not change the sense of the inequality. What that means is multiplying both sides of an inequality by the same positive number does not change the direction of the inequality sign. The direction of the inequality sign is the sense of the inequality. Let's solve 2w is greater than or equal to negative 10. I'm going to begin by writing down my original inequality. To isolate w, I need to divide 2w by 2. Dividing by 2 is the same as multiplying by a half, so our multiplication property of inequality says that as long as we perform the same positive multiplication on both sides of the inequality, the sense of the inequality will remain the same. Now you'll notice that the last symbol I wrote here was my greater than or equal to symbol. That's because when you start multiplying or dividing in an inequality environment, you need to be prepared for the unexpected. And you're going to see the unexpected here pretty quick. 2w divided by 2 is w. Negative 10 divided by 2 is negative 5. So my proposed equivalent inequality is that w is greater than or equal to negative 5. But we need to check this solution. I've gone ahead and graphed the solution set, at least the proposed solution set, on my w number line. It's all the numbers to the right of 5, and I also include the number 5, which is indicated by the solid dot. The first thing I need to do is check for equality at the endpoint of our solution set. So if w is negative 5, then the variable expression, which is 2 times w, equals 2 times negative 5, which is negative 10. So we do have equality at the endpoint of our solution set. Now we need to check for the proper sense of inequality at any interior point in our solution set. Since we have control over what point we're going to test here, we're going to try and pick a number that's going to minimize the chance of making an arithmetic error. And the easiest number to deal with from an arithmetic perspective is the number 0. So I'm going to check 0. If w equals 0, then our variable expression, 2 times w, equals 2 times 0, which is 0. So when w is 0, the expression on the left of my inequality symbol evaluates to 0. The right side of my inequality is always negative 10 in this case. So I have to consider what is the relationship between 0 and negative 10. Well, 0 is greater than or equal to negative 10, which is the proper sense given my initial problem. So this checks. I have a valid solution. So let's go ahead and state our solution set. The solution set, written in interval notation, the left-hand endpoint is negative 5, square bracket because we're including that endpoint. There is no right-hand endpoint, which I indicate with an infinity symbol followed by a rightward parenthesis. I could have chosen to write this solution set in set builder notation. I think I'll do that on the next example. Let's solve 3 is greater than 7x. 3 is greater than 7x, so to make x stand alone, to isolate x, all I need to do is divide both sides of this inequality by 7. Since I'm dividing by a positive number, the sense of the inequality is not going to change. This little unexpected thing that's going to happen, I'm giving you more and more clues. So when I reduce, what I'm left with is the inequality 3/7 is greater than x. Let's check this solution. The first thing I need to do is I need to graph my solution. So I have a number line, and I need to make sure my number line scale is going to allow me to plot my endpoint, which is 3/7. I need to indicate that this is an x number line, and then I need to indicate 3/7 on the number line. 3/7 is almost halfway between 0 and 1, but it's a little bit closer to 0 than 1. So there's my point 3/7. The endpoint is not included in the solution here because I don't have an equal bar in my inequality symbol. So I'm going to put an open circle at the point associated with 3/7. Now, my proposed equivalent inequality was that 3/7 is greater than x. That means that 3/7 lies to the right of x, so I need to indicate the points to the left of 3/7. And I need to put an arrow to indicate that this interval never stops. The first thing I need to check is for equality at the endpoint of my solution set. So if x equals 3/7, the variable expression, which is 7x, equals 7 times 3/7. 7 goes into 7 one time. 1 times 3 is 3. Both sides of the inequality are 3 when x is at our endpoint. So this check is satisfied. Now we need to check for the proper sense of inequality at an interior point in our solution set. So I'm looking at the interior of my solution set. I'm looking for a nice easy number to check. And the easiest number I could possibly check is 0. And lucky for me, 0 is in the interior of my solution set. If x equals 0, then our variable expression, which is 7x, evaluates to 7 times 0, which is 0. The left side of our given inequality is always 3. When x is 0, the right-hand side of our given inequality evaluates to 0. 3 is greater than 0. The sense of our original inequality was greater than, so we do have the proper sense when x is 0. Our solution checks. Let's go ahead and state our solution set. The solution set is, I think I said I was going to use set builder notation this time, so it's the set of numbers x with the property that, I'm going to go ahead and write x down first, and looking at my number line, I see that x is to the left of 3/7, so it's the set of numbers x such that x is less than 3/7. I'm going to finish up with one last example. Let's solve minus 3x is greater than 9. To isolate x, the first thing I need to do, it's actually the only thing I need to do, is divide both sides of the inequality by -3. Now some of you know what's going to happen, but I'm going to pretend like I've never encountered this topic before. And if I've never encountered this topic before, the natural thing to write here is that minus 3x over -3 is greater than 9 over -3. And this simplifies to the inequality x is greater than -3. So my proposed solution to this inequality is that x is greater than -3. So I've gone ahead and drawn my proposed solution set, all of the numbers to the right of -3. Let's check for equality at the endpoint of our proposed solution set. If x equals -3, then our variable expression, which is minus 3x, equals negative 3 times negative 3, which is positive 9. So we know we're at least half right. We have the right endpoint for our solution set. Let's check for the proper sense of inequality at an interior point in our solution set. So just to be different, rather than picking 0, I think I'll go ahead and pick 1 as our test point. If x equals 1, then our variable expression, which is minus 3x, equals minus 3 times 1, which is negative 3. So when x is 1, the expression minus 3x evaluates to negative 3. The other side of our inequality sign, the right side, it's fixed at 9. Now I need to ignore the problem I was given, and I need to ask myself, what is the relationship between negative 3 and 9? Negative 3 is less than 9. I do not have the proper sense of inequality. The left side is supposed to be greater than the right side. I have the left side less than the right side. This is wrong. Something is amok. Luckily, Candace knows something that evidently I don't know. So I'm going to turn it over to Candace so that she can talk about the negative multiplication property of inequalities.